Today we miss a little bit numerical theory, so it will be mostly the rest of the book. Well, not all of it, but this chapter 6 and 7. Before we begin, I am going to be away next week, so there will be no lectures. I had hoped to give you some guest lecture with multi-phase flow, but sadly he is also away, so you'll be on your own next week. I'll put out another exercise for you, so you have little to do, so you don't get so bored. But also you should start thinking about what you would like to do in your project work, and also then start forming groups among yourselves. The ideal group, I would say, is 3-4 students. That's a perfect group. And if you have other numbers, come and see me, then we can discuss it a little bit. What to do, that's totally up to you. So you can do whatever you want, actually, as long as I find it okay, suitable for this course. We are still missing some theory, and actually the most important part, which is then validation and verification. It's very easy to do a simulation and get some nice colors, but the question is, how good will your result be? You have to have something to compare it with, something to get an idea what's the overall attitude here. Can this be right? Can this be wrong? So that's clearly something that we still is missing. But that's something you need to sort of have in the back of your head already now, thinking about your project work. So don't invent some insanely complex and crazy problem that nobody has any idea what the result should be. That would sort of be quite hard to verify and validate that your result is okay. A lot of students over the years have chosen to pick some problem that they address anyway now with their projects. So that's a very good idea. Then you'll have a cheap chapter in your project work. I mean, you smack 2 flies in one blow, so that's also an option. After next week, I will then open up for you to come here on stage and then present your idea. If you are alone or just 2, you want to recruit some more members into your group, then you can have a minute here. You just present your idea, principal sketch on the blackboard, that's all, and see if you can recruit some more members. That is something that we can do in a couple of weeks' time. But start thinking ideas, getting ideas. What should we do? What can we do? I'll put out the last year's reports, what they did last year, so then you can have an idea of the what I expect from you. I mean, it will be 3 to 4 students, 12 hours work each week, and then for 4 or 5 weeks. That's what I expect. So the amount of work should also be shown in the report, of course. But more of that later. Any questions from you before we begin? Okay. So today the topic, chapter 6, chapter 7. And why? Well, we are not done with the input we have to give to OpenFOAM. Here it's a file called FV solution. So that's the last file, actually, input file that we sort of have to address. And here we have a lot of choices to be made, a lot of input. So we have some strange names, PCG, BICG, sometimes it will be an MG or whatever. And here we sort of have to specify which solver should be used here to solve the algebraic equation system. And also which algorithm should be used to solve the entire Navier-Stokes, the coupled problem, velocity and pressure all at once. So here is something called a simple algorithm, which we are going to address today. Here actually you see this non-orthogonal correctors. So that was the number you could play around with for the case where the mesh is not 90-degree angle. So you have some different angles in your mesh, then you should increase the 0 there to 2, 3, something like that. Also here, relaxation factors. So I will try to explain all this today. Now, I won't go through the entire book here, page by page. That's something for you can read yourself. It's pretty much the case, sort of the manual behind OpenFOAM. Not entirely, because you see here, he jumps directly to the staggered grid concept, which we talked about with finite difference and Sola. And the reason is that when you are seeking the solution for the velocity at one point in space, then in the Navier-Stokes you are going to need a pressure difference. So typically you use central space discretizing, and you use a pressure on each side of the velocity. But the pressure where you are standing doesn't enter into your discrete equation. So every other point will be one pressure solution, one pressure field, and the other ones then a completely different pressure field. And these two fields, they don't talk to each other at all. So that's the problem. You risk obtaining a checkerboard pattern when it comes to the pressure. And I think he has actually illustrated this here. So you see the checkerboard pattern here in 2 dimensions, 50 and 100. The 50s doesn't see the 100s and vice versa. So that is the problem. But the remedy in the 60s, 70s, that was then to use a staggered mesh, as we did with Sola. Remember, the pressure was in the center, and then the velocities were located on the cell faces. So that was one way around this problem. But in OpenFOAM, we know that inside one single cell, we have the pressure and we have the velocities. So that is the co-located mesh system. That's what we are using in OpenFOAM. So how can that be? Well, you have a trick called re-and-show interpolation to just avoid this. Sadly, the explanation here doesn't show up until chapter 9, I think. No, 11, chapter 11. So you can sort of skip or forget about the staggered mesh problem. We are going to use co-located mesh. So there is a way around it, and this is then what we are doing in OpenFOAM. So I mean, this is important to be aware of. Like in turbulent flow, when we were trying to find what's the distance in y plus units to your first velocity away from the wall. Okay, then you need to understand where is my first velocity. Well, the first velocity alongside the wall is going to lie in the cell center. So if you have a cell here, okay, then your first distance, well, the distance to the first velocity close to the wall will be delta y half in meters, which you then need to calculate the y plus and so on. Of course, this can be done for you in OpenFOAM. The pressure linked equation system. I will go through it a little bit in detail here. Simple, which then stands for semi-implicit method for pressure linked equations. And believe me, this is very it's very semi. You're going to do a lot of cheating here. So let's start out. If I write up the Navier-Stokes in, say, the x direction here, time derivative rho u, and then x derivative rho u squared. So here we have the convective acceleration terms written in the conservative form. And then y derivative rho uv. And then on the other side minus the pressure gradient in the x direction. And we have the viscosity and we have double derivatives. And gravity, if you like. Now from this equation system, the differential, or actually what we are doing now is the integral version of this one, integrate both in space and in time. Either way, you will end up with an algebraic equation system going like this. You have the center point coefficient, AP, and your unknown, now a velocity. In this generic explanation of these equations, we have always operated with the general unknown phi, which is now exchanged with the velocity, the unknown velocity, of course it is. And then these terms all of a sudden becomes nonlinear. Of course they do. Nevertheless, we have already cheated. If you can recall earlier, we had some examples with these, and then we wrote the convective terms as rho u phi. And here the dy of rho phi v. So, and now saying this phi, okay, that's the same as the velocity. These are not necessarily the same velocities. One of these velocities we use if we choose an upwind scheme, like a quick or muscle or any of the more advanced upwind schemes, to decide the direction of the flow. So, no, they are not necessarily the same. But forget about that. We just say that yes, we will have a whole bunch of algebraic equations like this, and typically the center point unknown velocity at point P multiplied with its coefficient AP equals now the sum of all the neighbors, a neighbor, velocity neighbors, and depending on the number of dimensions, 1, 2, 3, it can be a whole bunch of neighbors. And if you have an unstructured mesh system, it can be very many actually. Then we will have something coefficient and something with the pressure. And we might even have a constant here as well. So this will now be the algebraic equation system. How this one will be in detail depends on your choice of discretization schemes. But either way, this is one equation with too many unknowns. If you treat all the neighbors as known, okay, he is unknown, but also the pressure will be unknown. So let us start here. So inside here, this term, unknown, we start with a guess. We guess something crazy. P, what did we use here? P star. We guess P star. In an iterative scheme, of course, that will be the pressure from the previous iteration. In a time transient code, typically that will be the pressure from the previous time step. So the guess doesn't have to be that stupid. But it will still be wrong. So we need to adjust the solution here. So now we construct a correction equation for the pressure. The correct pressure, that is called P, equals this P star, and then a P correct. So the mark here means pressure correction. And then we do the same with velocity. Because solving this equation here, we will end up with some velocities that are not correct. And this should sound familiar to you guys. Thinking about Sola algorithm and the projection method, time splitting method. Calculate first a velocity based on the old pressure, then you get the wrong velocity, the tentative velocity field. It's the same here. So here U equals something wrong plus a correction, and same goes with V then. Like that. So what do we do? Well, this was the equation that we would like to solve, and sadly we can't. So, well, if we had the right pressure, yeah, that would be very nice, but no, we don't have it. So as with the Sola algorithm, we solve what we can. And we can solve this one. U P star equals sum of the neighbors, A neighbor, U neighbor, star, and then we will have this delta P something, star, and then plus B. So this was equation number 1, and now this is equation number 2. Subtract these two equations. 1 minus 2, what do we get? 1 minus 2. Well, then you see we end up with an equation system with center point coefficient AP multiplied with the difference between those two, which is the correction. So you end up with this equation here, AP U P correct. The correction equals, and then all the neighbors, U neighbor correction, and then delta P correction. The constant B, he will fall. Okay. Let's see, I don't think I need this one anymore, no. Still doesn't help. Still one equation with two unknowns. So we are not there yet. Now comes the first and dirty trick. We say this one is 0. Hey, oh, that's not 0. Of course it's not. But we do it anyway. this, what we are aiming for here is an algorithm that will work in the end. We don't care if we cheat to get there. And this is then the reason why it's called semi. It's very semi-implicit. So we just remove these terms. And then what? Well, now if we insert the equation system, it should then be possible to get the following equation. Let's see now. We will have this equation here, UP equals, and now this UP star. He's not a problem. This first calculation based on the guessed pressure and the guessed neighbor velocities. So he's just an explicit expression, so no problem to finding him. But now with this equation, you see we can rewrite this velocity correction, which is still unknown, in terms of the pressure. So what we get here will now be something like this: 1 over the coefficient, and then with something with this delta pressure correction like that. Okay. Still doesn't help. Still one equation with 2 unknowns. But then you do the same here with your V velocity equation, this one. You sort of substitute this velocity correction with the pressure correction, and then finally you use continuity. Of course you have to use somewhere along the line here the continuity equation, because I mean we started out with 1 equation and 2 unknown, you might say. So yes, we need another equation. So insert these 2, the velocities, insert into continuity, and then what we obtain, this will result in one simple equal equation for the pressure correction, P-float. So there you actually have the entire algorithm. And yes, it is very, very similar to the time-splitting algorithm, the projection method that we used in Sola. And if you do this with a uniform mesh, you will see that it is actually identical. It's exactly the same as the projection method. And yes, we also there used the continuity equation, if you can recall. So this will now be the standard simple algorithm. Then you have a whole bunch of variants. You have something called simpler, simplest, simplex, simple C, a whole bunch of them with small variation, small improvements. You even have, I think they use simpler here, if I recall correctly. Let's see. Simple algorithm. Yeah, simpler. It's a simple revised. Let's see. Another version here, since we are at this stage. Simple C. It's a popular variant. You take this equation and then you rewrite it a little bit. You take center point minus, and then you take the sum of all the neighbor coefficients and subtract on each side of your equation sign. UP flat equals, and then you have here the sum of all neighbors coefficients, but then you will get U neighbor, correct, minus UP, correct, and then minus or plus whatever delta P here. And then you do the same dirty trick, because from this equation here we need something that we can insert into the continuity equation, and in there we sort of substitute the velocities with the pressure. So here I say now this one is 0. Yes, it's wrong. It's just a dirty trick, but you see here, this is not so wrong as what I did up here. This is worse. This is definitely not 0. This one, at least, is a difference between two velocities. It's going to be closer than 0. So not so wrong as what we did up here. So it's actually a better convergence. Remember, in the end, we are talking about an iterative procedure, so you have to do this many times. But with some clever variants here, you don't have to use as many iterative steps as the first simple. You have other tricks. I won't go through all of them. It's going to take forever. At least there you have an idea what's going on.
One question.
Yep.
After iterating, all the methods should be correct. It only depends on
Yeah.
all the takes.
Yeah, they should, in theory. In practice, not necessarily. It's always like this. Like you see here, when you do this calculation, it's a small blackboard here. I think I've shown you this before also, like we had it with the Sol algorithm, the successive over-relaxation, if you can recall. So if you have an unknown, you use the old values and then you construct some adjustments to this quantity. And we sort of carefully calculate this adjustment to improve the old value to find a better one. So here, this could be then an iterative algorithm, could be a transient scheme or whatever. I mean, the philosophy will sort of be the same. What we then did in SOR, the successive over-relaxation, we multiplied here with an omega and said omega should be between 1 and 2 to improve or speed up the solution process. And finding a good omega, that was actually a very good idea. It really speed up the process. Omega equal to 1, then we had the classical Jacobi or Gauss-Seidel iterations, as we call them. But now, when you have a very coupled equation system, we are talking about under-relaxation. Here they use an alpha. So for the pressure, P equals P star plus this correction that we have just calculated now from the continuity equation. Then we multiply him with an alpha for the pressure. And this alpha can be a very small number. So we sort of find the adjustment, but we don't dare to take the entire correction. We just take 10% of it. So alpha here will be a number between 0 point something and 1. And typically he will be smaller than 1. Try to use a number bigger than 1 to speed up the process. Things will explode in your face. Just try it. because these numbers are something that we have as an input option into the code. If you can see here, relaxation factors for the pressure, they use only 30%. For the different velocities, they use 70%. So typically different from pressure to the other variables. What's a good number here? Hard to tell. It will depend on actually your problem. So you do this by just sort of soften things down a little bit here when you do the update of your unknown, because the corrections may be too big. Remember, it's a nonlinear equation system here, so yes, we have to do many iterations, and we have to do it carefully, slowly. You can't take too much adjustments at a time. So here you may actually have to use smaller numbers if you have a very complex problem that explodes all the time, no matter what you do. Then maybe you have to go down to 10% or something. So that's sort of the simple algorithm. We have another one. I think it's called, we have several. Some is called Pimple. And here they have something called a piezo. Let's see if we can find it. Algorithm for the simpler. You can have a look if you like. And here the simple C. And here the piezo. It's sort of the same as the simple philosophy, but you have an additional step. So you have a predictor and corrector step as well. So then you see you will have some additional equation system here. So it's getting rather messy actually, double star, and the notation can be confusing. So just think of it as a little bit more advanced simple. So piezo, that is absolutely also an algorithm that you will find in OpenFOAM. Yeah. So it's just an additional step. So here, general comments. You will have a little bit more CPU, a little bit more calculation. Here, for simpler, for instance, 30% larger than for simple, but then the computer time is still reduced. So it might be a good idea to not use the traditional classic simple. It's a little bit too primitive, a little bit too simple. They have an example here, and it's rather boring, so you don't have to look through this. Let's see what we end up with here. I don't think he accesses any others. No, it's just a summary. Yeah. So next we will then jump to solution of discretized equation systems. So now we are into the world of pure numerics. We have an equation system, and we want to solve it. We want to solve it as fast as possible. Any questions so far? Okay. So for the equation system, you can always write it like this: AX equals B. A now being a complete coefficient matrix. X, all your unknowns, velocities, pressure, whatever. B, constant or not constant, right-hand side of your equation system. The coefficient A is going to be very, very big. So A here will typically be a band matrix, something like this, but mostly zeros. So you will never store the matrix A in memory. Why should you store all these zeros? So you only store the coefficients that you need. So here, all your unknowns, x1, x2, yada yada yada, down to xn equals, and then you have same on the other side, the b's. How to solve this one fast? Of course, the obvious solution here, use a direct method. You just find A inverse. So x equals A inverse B. Problem done, of course. That's obvious. But if you have 1,000 unknown velocities, 1,000, that's not so big actually, 1,000 cells or something like that, or 300 cells, you will easily have 1,000 unknowns. Then the A matrix is going to be a 1,000 by 1,000 matrix, which of course you don't store, as I told you. Most of it will be zeros. So that's not a real big problem. But this one is a problem. A inverse, that's going to be a full matrix. There you blow the memory of your computer. You can't store this amount of numbers for a real case. So using matrix inversion is actually not an option. It will blow the memory sooner or later. And also it's a lot of work to find this A inverse. So yes, would be nice, but sadly no. The memory here is overwhelming for a real problem, for any real problem. What he starts with here is something called TDMA, it's a Thomas algorithm, solving an equation system if you only have a 3-diagonal matrix. If it's only 3 bonds, that would be a one-dimensional problem. Then yes, it's possible to solve this one directly without any storage, and that's not a big deal actually. So at TDMA, yes, that is not a problem. Well, then we can use TDMA to construct an iterative scheme. How is that possible? Well, the way to think is the following. Here I have now a 2-dimensional case. So I have, say, 100 by 100 unknown or something. And I want to solve my equation system, which then is a very big one. So how do I do it? Well, if I look at a line here in the x direction, anywhere here is a line. And then I say now, along this line, I will have, say, 100 unknowns discretely distributed along that line. And then I say, these are my unknown. And I treat the rest of the field as known. Remember, the equation system will, of course, then also include the neighbors here, up and down from this line. But I don't care about that. I sort of treat them as known. And then I just write the equation system here for this line alone. So a line solver, he will actually use this Thomas algorithm for one single line throughout your domain, and just solve it here. It's very easy to solve, it doesn't take much CPU. It's a direct method for this line alone. Of course, it's not correct because, I mean, now you're treating the neighbors as constant. You just put them on the other side of the equation sign. And they are, of course, not the correct velocities. So to find a solution, you have to do it for one line, then you do the next line, then you do the next line, and so on. So you sweep over the entire field line by line and solving this TDMA equation system. What you also then should do is to use line in the other direction as well. some alternating directions implicit ADI methods, quite popular, and that will sort of ensure that you will actually get a solution, because this is going to be a little bit dependent on your geometry, if the delta x is bigger than delta y, what is the flow direction here. I mean, the information here can travel quite fast along these lines when you solve it like that, but you should use every other line as well and think in both directions here. So yes, with this TEDEMA, it's possible then to find or set up an iterative solution algorithm, and that is not so tricky and fairly easy. You have the recipe here. Even in 3 dimensions, yes, it's also possible. Line like this, and then line in and out of the blackboard. That's also an option. And yes, it works. And yes, it has been done with some success. Very easy, and it doesn't blow the memory, but it's not the best solution algorithm, of course not, but it works. Takes some time, but you will get there. Yeah, I won't go through all this. It's not the fastest, but yes, it will actually work. And also with this algorithm, you could do the same trick as we did with SOR, over relaxation. There you could use an omega with a number bigger than 1 to speed up the process. You could at least try. So TEDEMA, not the fastest, but it works. Okay, we continue with point iterative then after the break. Any questions? Then we take a break.